Okay, cool. Hopefully we're recording now. The other thing that I wanted to say, as far as announcements go, is you all took your first skill quiz on Friday. Thank you so much for doing that. I felt a little bad turning around and giving you a quiz on stuff that we had just talked about earlier that morning, but you all rose to the occasion in flying colors. So thank you all so much for doing that. I wanted to briefly talk about the quiz and what the different grades mean, because in a sense, the Friday quizzes will form sort of an important element of the course itself. And I want to make sure that we're all clear about what's sort of expected of them and what you do depending on what grade you got. So these quizzes are mastery based. You might have noticed that in Moodle, it's graded as a score of either 1 or 0. And you just get a score of 1 if you've mastered the quiz, a score of 0 if you still have some work to do. And then at the bottom, you can see there are different places where I can circle your grade. Your grade will either be a grade of mastered, a grade of progressing, or a grade of requires reassessment. In short, a grade of progressing means that you have most of the material and you have a strong sense of the skill. But there are still a few small elements that you're missing out on, right? And so in that case, what I'm going to ask you to do is, and let me back that up a second, a grade of requires reassessment just means that there's something a little more fundamental that you didn't quite display on that first pass, and that I want you to take another quiz sort of similar to that one, in order to show that you have gone back, revised it, and reviewed it, and have mastery. The only grade that counts in the end is a grade of mastered. So if you still have a grade of progressing or requires reassessment, there's still a little more work for you to do. But the hope is that all of the work should be relatively low stakes. The quiz you saw, I mean, hopefully it was a relatively short quiz in the sense that it didn't take you more than 10 or 20 minutes. And then the hope is that the reassessment will be equally short. So if you got a grade of progressing, here's what I would like you to do. I am going to post a full answer sheet to that quiz on Moodle. It's not quite up there yet. It was my goal to get it up there this morning, but that didn't quite happen. So it will be up there, I'd say, by 10 a.m. this morning. And I'm going to put it right here. Nope, right here after the quiz 1 that was to be taken last Friday. So I'll put the solutions there. If you got a grade of progressing, what I'm going to ask you to do is to write up your solutions to the quiz in your own words. Feel free to use the solution key or not. But the idea, again, in a progressing is that you are very close. There's just a small misconception. So using the answer key or not, but try to identify where the misconception is, write up full solutions, and then write a very brief, I'm calling it a reflection, but write a very brief statement. It can be as short as a couple sentences, just saying, you know, here's the correct work. I had it all right except for this thing, which I didn't completely understand at the time. So write up those solutions as well as a brief statement, just sort of talking through your thought process, and email that to me. So just send that to me as an email. I'll go ahead and update the grade in Moodle to reflect your mastery of that skill. I'm going to ask you to do that by the end of the calendar week, and I'll remind you about this as we go forward. So by the end of, I guess, by Friday, I'm going to ask you if you got a grade of progressing to send me that email. If you got a grade of requires reassessment, that's also A-okay. That just means that there's a little bit more that you have to go back and review. But I'm going to ask you to take another reassessment quiz on the upcoming Friday. So you notice in Moodle, we have our next set of things lined up. We had the video to watch for class today, the video to watch for class on Wednesday, the video to watch for class on Friday. And then on Friday, there will be the next 2 skills, next 2 quizzes to be completed, as well as if you got a grade of requires reassessment, you'll be asked to retake a quiz 1 at that time. So any questions sort of right off the bat, any questions about either the system or what's expected of you? All right, a question I get a lot, not to put words in anybody's mouth, but a question I get a lot is like, are you penalized for multiple attempts? So if you had to do like a requires reassessment and you take it again and you get a requires reassessment again and you take it a third time, like, are you penalized for that? And the answer is absolutely not. All I care about at the end of the semester is, I mean, I care about a lot of things, but I care about like, have you mastered these skills that are part of Calculus 2? So I don't care if you master it on the first pass. I don't care if you have a couple bad weeks and have to double back and study again and then master it in late September or mid-October or early December, right? As long as you're leaving the semester with this mastery, I'm really happy and I want to give you a grade that reflects that. So it's supposed to be very forgiving and it's supposed to also encourage the fact that these quizzes are low stakes. All right, so I did want to clarify that. So if you have questions about what is owed of you, sort of specifically, please feel free to reach out to me, talk to me after class, or send me an email. I'm very happy to talk about that. I think that was my only announcement. Let's go ahead and turn to the item pool really quickly to check in. Looks like a number of you have subscribed, have answered. Right, we're talking about the Star Wars trilogies. There are 3 trilogies. Which one is your favorite? Looks like there is some general consensus, maybe not quite consensus, but some general thoughts about, I haven't watched enough of them to form an opinion. That's quite fair. And then everybody else is sort of split between the original trilogy and the prequel trilogy. No votes for the more recent Disney movies, I think is telling. All right, I love it. Let's pivot. Thank you all so much for taking the time to do that and for checking in. Let's pivot towards talking about calculus. And specifically, the topic for today is this topic of integration by parts. It's our second integration technique. And in the video, we introduced the idea behind integration by parts, sort of ending with this formula right here. The formula suggested that if we ever have an expression of the form u times v prime, so we're trying to integrate a product of 2 functions. We have one function u, which we identify as a function u of x, and another function which we identify as the derivative of a function. So we identify it as v prime for some other function v. Then the integration by parts formula says that the integral of u times v prime was u times v minus the integral of v times u prime. We gave a few different ways that we could write this. This is the official formula. A sort of slick shorthand way that we can write it was given up here. The integral of u dv equals u times v minus the integral of v du. So here, as we mentioned briefly in the video, this formula is suggesting that this dv, that's sort of a stand-in for v prime times dx. Actually, as I say that, I realize I have it written just up above, right? So the v prime times dx can be shorthanded as a dv. The u prime times dx can be shorthanded as a du. And then we end up with this sort of shorter formula here. I mention it in part because when I was a high schooler, my professor said that he had been taught, he remembered the formula as the ultraviolet voodoo formula, and he said that this was ultraviolet, right? So u times v, ultraviolet, v du, voodoo. Right? Just as a sort of mnemonic device of some sort. And I think it's pretty silly, but for the life of me, it's been about 15 years or 20 years, and I've never forgotten it. So I guess if it's silly, but it works, I wanted to share it with you all as a potential mnemonic device. The formula comes from, as we saw, the formula comes from this observation of the product rule, and specifically that if we have the expression u times v, so if we have 2 functions, u times v, and we go to take their derivative, the end result by the product rule was u prime times v plus v prime times u. This is just our good friend, the product rule when it comes to taking derivatives. And so as a result, then, we end up with, or I guess we can rewrite this as, let's try to write this correctly. I'm going to keep this piece on the same, on one side of the equation, and I'll subtract the u prime times v. So we end up with v prime times u equals the derivative of u and v minus u prime times v. And notice the similarities between these equations here, right? One of these is just a formula involving derivatives. The other one is the equivalent formula involving integrals. So this integration by parts formula came from this, this product rule, as we sort of saw in the video. So just as a quick check-in, I'm still trying to figure out the best way to effectively use the item pool, besides just a morning check-in. So as a quick check-in, let's see if this works. We have a formula that we know is true by the product rule, right? So we know that if we take x times e to the x and we take its derivative, the end result is e to the x plus x times e to the x. So which of the following could be the corresponding expression that might come about as a result of integration by parts? And we have three choices here. So take a moment to look over that and vote on what you think is the integration by parts formula that would arise in this case. Okay, let's take a look. We've got a number of answers here, a couple different answers. Let's give it another 15 seconds, and then we'll go ahead and view the results. Okay, that might be just about everybody. I think there seems to be some general consensus around one of the answers, around answer C, with a couple people saying A. And I think C is the correct answer, but let's confirm that and try to see why that's the case. So in particular, for question C here, or for answer C, on the surface level, it has the correct sort of integration by parts form, quote unquote, in which we have an integral of some sort equals a function minus a second integral, right? And if we go back to the integration by parts formula, we notice that that is the general form, right? One integral equals a function minus a second integral. But more than that, we can actually identify what corresponds to u and what corresponds to v in this expression. And specifically, I've lost it, there it is. Specifically in this case, we can identify that our two functions were x and e to the x, and that our x is actually playing the role of our u, while the e to the x is playing the role of v prime. And we'll talk a little more about the roles of u and v prime here in just a second. A is a great answer. It looks similar, but it turns out I think there's an issue with a negative sign here, right? It also has the x e to the x on the one side, and that equals a function along with another integral. But I think this integral should ultimately be subtracted in order to make it correct here. All right. So when it comes to this integration by parts, then, one thing that we've noticed is it doesn't actually solve the original integral completely, right? If we're ultimately asked to find an antiderivative of u times v prime, it doesn't give us the answer straight up. Instead, it gives us an expression minus a second integral. And one of the hopes in using this formula is that we can then go on to solve the second integral by more streamlined means, or that it's a more straightforward integral to approach. And that means that there has to be a little bit of educated guess and check and a little bit of artistry in trying to pick the u and the v prime, the expressions over here, that give us the appropriate second integral over here. And we have some hints here on how to choose a u and a v prime. So we try to ultimately choose u and v prime. We choose u so that the u prime is simpler than u originally was. So if possible, we try to choose our function u so that its derivative is simpler than the original function. And there's a list here of potential good choices for u. That includes logarithms, inverse trig, algebraic expressions, and then trig, and then exponential. And maybe I should say, in some sense, this is an ordered list. The trig and the exponential typically don't simplify. The u prime is not any more simpler than u is. Right, the derivative of e to the x is e to the x. The derivative of a trig function is another trig function. So it usually doesn't simplify down as nicely as some of these other ones. And that's u. So v prime, though, we often choose v prime so that its antiderivative can be easily evaluated, so that we can ultimately figure out what v prime is. And that will be important when we're applying the formula. Notice the formula requires us to plug in a v, which means that we'll need to figure out what the antiderivative of v prime is. So we'll need to be able to figure out what it is. And so these are typically our guiding principles, I should say, for when we're picking our u prime and our v, or our u and our v prime. So let's take a look at an example. We've already looked at something kind of similar to 3. So I want to pivot down and take a look at 4. We'll sort of talk about this as a class for a moment. So in this one, we have a function that we're trying to integrate. It's 2x times sine of x. And what we expect is that this might be approachable using integration by parts. We don't immediately see how we could integrate it otherwise. We could try u substitution, and we're welcome to, but trying a few guesses of u, we don't see any good choice of u for the u substitution process. So we can make the executive decision that what we really want to try is an integration by parts. So we can do integration by parts, which means that we're going to be using the ultraviolet voodoo formula, right? So the integral of u times v prime, or to write it in the ultraviolet way, the integral of u times dv equals uv minus the integral of v du, right? i.e. u times v prime equals uv minus the integral of v times u prime. So we have both of these formulas. We can choose our favorite form. What that means, though, is that this expression, the 2x sine of x, should align with the u times v prime. And then it's up to us to figure out which of those pieces corresponds to a u and which of those pieces corresponds to a v prime. So we can go back up and think about which choice might make the most sense. Again, there's an element of educated guess and check here. According to our list, we want an expression for u that gets simpler as we take its derivative, while for v prime, we want something whose antiderivative is well known. So if we sort of make a little dividing line here, we can see that either of these could fulfill the role of v prime. We know how to integrate both of those, but it's the 2x that gets simpler when we take its derivative, right? So it seems like a decent educated guess could be to let u equal 2x. And at the same time, to let v prime equal sine of x. Now, at this point, according to our formula, we will need to be able to plug in u, v, a v, and a u prime. So that means that we actually need to compute, based on this choice, what is u prime? And here's why we want this to get simpler, right? U prime is just 2. It's pretty simple. And we also want to know what v is. And here's why we chose v prime to be integrable. We can calculate v prime, or I'm sorry, we can calculate v as the antiderivative of sine, which is not cosine, but negative cosine, right? So this becomes a negative cosine. And now, according to our formula, right, our integral, if we're originally interpreting this as a u times v prime, we would get that the integral of u times v prime, so the integral of 2x sine of x equals, and now just using the formula straight up, it's u times v, so that's a 2x times negative cosine of x minus the integral of v times u prime. And so notice what we have now is an expression that still involves an integral. Let me write it here. This is negative 2x cos x plus the integral of 2 cos x. So we didn't completely solve this, Gesundheit. We didn't completely solve this. We started with an integral. We still have an integral, but this second integral is now much more straightforward, much easier to compute. And so what we get there is that this should just equal negative 2x cos x plus, and then the antiderivative of cosine is positive sine. So this becomes plus 2 sine of x plus c. Right? So when it comes to integration by parts, the key sort of steps involve figuring out what we thought the right u and v prime were, calculating the derivative of u, calculating the antiderivative of v prime, plugging everything in. That was this step right here, right? So plugging everything in to the integration by parts formula that took place there, and then actually solving this second integral, and we end up with an answer that we're reasonably happy with. Actually, we're quite happy with it. Any questions about this? Any questions at the moment? All right. So the truth is, this is really the whole game when it comes to integration by parts. There are a few sort of interesting wrinkles which we can uncover through the sheet, but these are sort of the big, or this is the big important approach that comes with integration by parts. It's all about that formula and then figuring out what your good choice of u and v prime should be. So what I want to do, we're here a little bit, we're just under halfway through our class. I want to pause and give you all a chance to work on some problems. I'll pause the recording while we do that. Resuming the recording. So we have these two possible ways to solve problem 5. I agree with the group's consensus that the red one is right, but I want to throw in a little asterisk. Both of these formulas are correct, right? The integration by parts formula works in both of these cases. And so in fact, what we have here are two equivalently correct equations. One that says the integral of x squared sine x is equal to this red thing up here. The other one, which says the integral of x squared sine x is equal to this blue thing down here, and both of those are true statements. That being said, I like the red one more. Why do I like the red one more?
The blue one will never be able to get down to, never be able to integrate. So the one without integration.
Yeah, so the answer that was given, which I completely agree with, is the question of where do we go from here? And in particular, both of these answers have an integral in them. So where do we go from here? Well, we'd like to be able to compute that second integral. And the answer that was given is that this red integral is going to be easier to compute than this blue integral down here. And that's absolutely true. How would we integrate this, this one up here? How would we integrate that? Yeah, look at how similar this one is to this one up here, right? They're not quite the same. There's the sine versus cosine, but they're very similar. So how would we integrate that red one? Well, we would just play the same game. We would integrate by parts again. And the end result is that this 2x, just like up above, would become just a 2. And we would end up being able to solve the final integral. So following the same blueprint as above. On the other hand, what we've done down here is we've let that x squared turn into an integral involving an x cubed, and that's getting more complicated, right? That's becoming a more challenging integral to compute. That's sort of going in the quote unquote wrong direction. So what we have in the blue is a correct formula, but one that doesn't help us functionally because we don't know how to integrate that x cubed over 3 cosine x any better than we knew how to integrate the x squared sine of x that we started with. Okay, all right. Okay, that's all I've got. Let's pivot here. I'm gonna try something a little new. Let's just see how this goes. We have a few different problems here, all of which are worth working on. I want us to sort of divide up the room a little bit. So I'm gonna ask maybe these two columns. Can you all work on problem 6? Maybe work on any of the problems, but start with 6 and see how far you get with 6. I'm gonna ask this middle column here. Can I get you all to work on 7? And can I get this group over here to work on 8? And I should say, feel free to jump around, but start with that one, see how far you get before you get stuck. And for problem 8, I have a clue. For problem 8, I'm gonna say, try writing the integral of ln as the integral of 1 times ln. And see if that helps at all. I'll pause the recording and we'll check in again in about 10 minutes to see which of these we want to talk through the most. So let's resume our recording. We're taking a look at problem 6 here. And to begin again, we'll need to try to figure out what should be a good choice of u and what should be a good choice of v. And it seems like a potentially nice dividing line is x squared times ln of x. So let's take a look here. In order to solve this, right, going back to our guiding principles, we would want to choose a u that gets simpler as we go, and we would want to choose a v prime that gets that's integrable, that we know how to find an antiderivative of. And here, those things are kind of in conflict with each other. The x squared arguably gets easier, right? X squared goes to 2x when we take a derivative. The ln of x goes to 1 over x as we take a derivative. But the big issue is we might not remember how to find an antiderivative of ln. So projecting ahead, if we set this as v prime, then we would ultimately need to find v, which means that we would need to know what the antiderivative of ln of x is. And we might not know that. In fact, let me erase this for a second. In fact, we won't know that until we get down here to problem 8. Right? We won't know what the antiderivative of ln is. So if we happen to know ahead of time, could we give that a try? Sure. But I'm going to recommend that we actually let our u be ln of x in this case. So u equals ln of x. That means that u prime will equal 1 over x. And that leaves our x squared to be v prime. Sorry, I should have written v prime equals x squared. And when we go to find its antiderivative, we get something more complicated, which is less than ideal. We get x cubed over 3. So with those choices, our formula becomes the integral of u times v prime becomes u times v. So that's ln of x. I should say the entire thing was equal to ln of x times x cubed over 3 minus the integral of v times du. So that's x cubed over 3 times 1 over x dx. Okay, and just like in our previous problem, what we have here is a completely correct formula. We've just used the integration by parts formula. But the question becomes, is this any better than what we started with? Can we integrate this new integral in a more straightforward manner? And thankfully, this time, the answer is yes. The secret is that we have to recognize, I'll stick with blue here, I'll go green. We have to recognize that rather than leave these things separate, we are much better off combining them into a single expression, right? X cubed over 3x, which can be simplified to x squared over 3, right? So we have an x cubed up top, we have a 1 over x, so we have an x in the denominator, and that actually simplifies down really nicely. So what we actually have here is we have the ln of x times x cubed over 3 minus the integral of 1/3 x squared dx. And that integral we can just compute regularly, right? The x squared would itself become an x cubed over 3. So the original integral equals this integral up here, which got rewritten to become this integral here. And at this point, we can actually compute that second integral. We get ln of x times x cubed over 3 minus, we still have the 1/3, right? That constant just floats out there. And then the x squared becomes an x cubed over 3 again. And so we end up with this thing. And maybe written in its nicest form. Slide over here. This becomes ln of x times x cubed over 3 minus, and that's just 1/9 x cubed. Okay, so we simplified it a little bit. What we have found here now is the antiderivative that we were originally looking for. But we haven't yet, I'll slide back in just a moment, but I just want to remind us, we haven't yet addressed the bounds of integration, the 1 and the 5, which means now that we have found our antiderivative, we'll have to plug in appropriately. So let's go back. Here was our antiderivative, right? This was our f, capital F. But what we know our definite integral should be, it should be capital F of 5 minus capital F of 1, which means that we have to take all of this, plug in 5, see what we get, and then subtract all of that when we plug in 1. And the way that we typically denote this, right, as a reminder, the way that we typically denote this, we have found the antiderivative. And then to denote this appropriately, what we'll typically do, the worst part of this app is its eraser tool, which sucks. In order to denote this appropriately, what we'll typically do is we'll put brackets around this. We'll put a 1 and a 5. That's just sort of signaling to whoever's reading your work that we've found the antiderivative, and now we're going to evaluate by plugging in these bounds of integration. So what we get then, and again, we'll just formally write this out, and then we'll leave it as is. When I plug in the 5, I get ln of 5 times 5 cubed over 3. So that's 125 over 3. Right? 5 cubed is 25 times 5. Minus 1/9 times 5 cubed. So that's minus 125 over 9. That's our f of 5 right there, minus our f of 1. So that's ln of 1 times 1 cubed over 3. And remember, ln of 1 is 0, so that whole first term is just 0, minus 1/9 times 1 cubed, so minus 1/9. And we're done. We could simplify this. We could absolutely simplify this, but I'm happy for us to leave our answer like this. Is it ugly? Yes, it's miserable, but it's correct, and we're confident that it's correct because we went slow and we're happy with our integration by parts. Let's take a big breath. Any questions about that? Okay, so this just about brings us to time with my final minute and a half. A few quick announcements just to wrap things up. First of all, just because 12 of us voted that we wanted to see problem 6 doesn't mean that there wasn't general interest in problems 7 and 8. Those are absolutely worth talking through. And so I would encourage you all to check in on the community hub and to share those answers there, especially if you were one of the groups. So like the middle column, you were looking at, I want to say problem 7. You all over here, you were looking at problem 8. If you want to fill in your answers there on the community hub so that we all have access to them, your classmates will greatly appreciate that. The final thing I wanted to just say again, I said it at the beginning of class, but as a reminder, for those of you who took the quiz over the weekend, again, thank you so much for doing that. If you mastered it, you are good to go. Nothing else needs to be done. If you got a grade of progressing, I'm asking you to submit some corrections along with a very brief reflection, and the details there, well, I should say the answer key will be posted to Moodle within the hour. So if you want to look at that as a reference, it's there for you. Otherwise, have an absolutely wonderful rest of your day. I'll go ahead and stop this recording.